Welcome to Oscillations. Today we are going to talk about the eigenvalue equation and the principal axis transformation. Previously we derived the set 6.8 as second-order linear differential equations of a form familiar from electrical circuit theory. The general solutions of such equations are complex functions, though only the real parts represent actual physics, and they are written in the form 611, where the c's are just scale factors and the a's of index I are complex amplitudes of the oscillation. And plugging these solutions into the set of 6.8, we obtain the corresponding set of algebraic equations given here for the complex amplitudes, the elements of the operators v and t, and the squared frequencies. So these are n-linear homogeneous equations for the complex amplitudes, and they will have non-trivial solutions only if the corresponding determinant vanishes. I've written it in an expanded form here. So what this symbolizes is an algebraic equation of f degree for the squared frequencies, and the roots the roots of the corresponding equation provide the frequencies for which the set of functions 611 are correct solutions for the equations of motion 6.8. And for each squared frequency, the set of equations 6.12 can be solved for n-1 amplitudes in terms of an arbitrary member of the set A of index I. And you can see that 6.12 is entirely equivalent to an eigenvalue problem that is more general than the one we discussed for rigid body motion. Namely, it's an eigenvalue problem where the action of the operator v on the eigenvector A is not just proportional to the vector itself, but rather is proportional with the action of the operator t on the same vector. And before studying this eigenvalue problem in more detail, we will first show that both the eigenvalues and their corresponding eigenvectors are all real. To see the proof of reality, we can write the eigenvalue equation for a specific eigenvector k and its corresponding eigenvalue. And then if we were to assume that the solutions were complex, then we could write the Hermitian adjoint of this equation for some other vector, let's say of index L, in the form here. And this holds because, as we have seen, both the operators v and t are real and symmetric, and as such they are equal with their Hermitian adjoints. And from these two expressions we immediately obtain the following results. So this one we can multiply with the Hermitian conjugate of the vector L from the left, and this one we can multiply to the right with the eigenvector of index k. And then if we just subtract them, we obtain the equality here. And if we now, going further, we impose that the two indices are equal, then we get this equation. And we see that it holds immediately for real eigenvalues, but we would like first and foremost to show the reality of the number here obtained by the contraction of these eigenvectors on that's the contraction of the operator t for these eigenvectors. And in order to do that, we simply assume that the eigenvector of index k is complex, and if that is the case, it can be expanded in real and imaginary components involving two real vectors alpha and beta, where beta is multiplied by the imaginary unit. And as such, if we just expand the product here by using this expression for the vector A, we obtain the sum of three terms here. where the imaginary part vanishes by virtue of the fact that within the parentheses we are taking the difference of two numbers, which as you see, these two numbers are just one is the complex conjugate of the other. But as both of these vectors, alpha and beta, are real, and given that the operator t is real and symmetric, it means we are just subtracting one real number from itself. So this result is 0, and as such, the product here is real. Furthermore, if we go back to result 6.6, what it implies is that the kinetic energy of the system is this particular contraction, and as such, each of the first two terms in equation 619, so this one and this one, are both twice the kinetic energy if we make the identities here. So we identify alpha and beta with the dot product of with the generalized velocity vector k, right? So then, as the kinetic energy is by its nature and by its definition positive definite, it means that this number cannot be 0. And then if we go with this conclusion back in equation 618 here, this proves further that not only is this contraction real, but the eigenvalues corresponding to the eigenvector of index k, the eigenvalue is also real. Now, another consequence is that the ratio of eigenvector components must also be real as a consequence, and this leaves us with one final arbitrary component for which we may simply make the reality requirement. So we want it to be real, in effect stating that any complex quantity that could be involved, it can just as well be hidden inside the scaling factor c of this solution in equation 611. Going further, we can solve 615 for the eigenvalue in order to find lambda of index k as the ratio of these two contractions. And now the numerators is either positive or 0 due to the requirement that we are studying physics for systems close to stable equilibrium. The denominator itself is positive definite, and as such, lambda is either finite and positive or 0. Now, as lambda is the square root of frequency, it means that a positive value corresponds to real frequencies of oscillation. While if we are away from a local minimum, the numerator might be negative, which would lead to imaginary frequencies and unbounded motion. And this is the formal proof of the statement that a minimum of the potential is required for stable motion. So it's contained in the expression here. Now, 617, taking into account the reality of the involved eigenvalues, can be written in this form. And then, in the case where the roots are all distinct, then this equation can hold only if the contraction here is 0, in the case where L is different from K. So this is really a kind of orthogonality condition, but it's a bit more abstract than the orthogonality in, let's say, in the simple Euclidean space, where we would take this kind of contraction with respect to a trivial metric tensor. The metric of configuration space can be a bit more complicated, that the geometry can be more complicated, and this is contained in the structure of the operator T entering the orthogonality condition. So on the one hand, the equation here implies this, but for going further, we can also fix all of the components of the eigenvectors by demanding that they are normalized. So we are demanding that this set of equations that this particular equation holds. And then there are n such equations, so there's one for each eigenvector, and each of them fixes the last undetermined component for each of the n eigenvectors A of index k. The set of results contained in equations 622 can be written in the form of a single matrix equation involving the transformation of the T matrix through the matrix of eigenvectors and its transpose. But the argument leading up to it fails if not all eigenvalues are distinct, and this is the case of degeneracy. However, as we will show a bit later, such a suitable set of eigenvectors can always be constructed, so even in the degenerate case. When we have studied rigid body motion, we made use of similarity transformations, which were defined by the equation 441 as written here. The kind of transformation that is involved now in the study of small oscillations is known as a congruence transformation, and it has the definition here, where of course there is a prime index missing from the C. And notice that in the case of orthogonal matrices, so if the transpose of A happens to be equal of its inverse, then the congruence transformation is entirely equivalent with the similarity transformation. And in effect, what result 623 says is that the matrix of eigenvectors A transforms the matrix T by congruence into a diagonal matrix. Now, if we can write the eigenvalues in the form of a diagonal matrix, and then if we take this this way of writing them and we bring it back to equation 615, we obtain the matrix equation here. And the reason we write it in this way is because if we multiply it with the adjoint of A with the transpose of the matrix A from the left and use the result 623, so the congruence transformation given here, then we obtain the congruence transformation of V. So transforming the operator V through the eigenvectors matrix by congruence brings it to the diagonal form lambda, where this matrix has just the eigenvalues on the diagonal line. So this is equivalent with writing the eigenvalue problem in the form of a secular equation, where we need to calculate the determinant of a matrix given by the difference between the diagonal form of the operator V and the eigenvalues matrix. So in effect, we have reduced the general problem to solving two matrix equations, which are the corresponding congruence transformations of T and V through the matrix of eigenvectors A, leading on the one hand to the identity matrix and on the other hand to the diagonal form of the potential matrix. Now, it should be noted that there is an alternative to this method, which involves using the so-called mass-weight normalized coordinates. And the advantage is that for this approach, the matrix of the kinetic energy is just the identity matrix right from the very beginning. And in this case, the eigenvalue problem is entirely analogous to that of the inertia tensor in rigid body dynamics. The only difference being that now we are in an n-dimensional configuration space as opposed to the 3-dimensional Euclidean space that was implied there. So the equations reduced to the orthogonality condition for the eigenvectors matrix and the congruence transformation of V, bringing it to the diagonal form here. So this approach has the advantage of simplifying the mathematical calculations, but however the The problem is that it can obscure the physics, given that different coordinates can have different characteristic scales. So it's an approach that generally I will not, for the most part, I will not use in these discussions. In order to make things hopefully a bit more clearer, we can look at an example, namely a particle of mass m moving in a plane having two degrees of freedom x1 and x2. So then the Lagrangian is just the kinetic energy of the particle minus its potential energy, where the components of the matrix, of the V matrix, are some unspecified constants for the time being. And then immediately from this Lagrangian we can write the secular equation right away. And upon solving it, we obtain the two roots of the equation, so lambda 1 and lambda 2. And furthermore, we know that the eigenvectors need to satisfy this set of equations, so the equations here plus the normalization condition, where in the first case the summation is only over the index j. And now we can study this problem in more detail by looking at two limiting cases. For the first limit, we have distinct positive diagonal elements of the matrix V, and we have constant off-diagonal elements that are non-vanishing but much smaller than the difference here. And we will use the small quantity delta given by this ratio in order to find approximate formulas for the two eigenvalues. So immediately, just by using these definitions and conventions, we can write, for example, the first root it immediately gets the form here. And now the square root is of this kind, and we can expand it to Taylor series in the second order. We should obtain this result, and as such we can find for the two roots the approximate expressions here. Furthermore, we can also calculate the eigenvectors, and if we go to the second order and delta, so using the set of equations here together with the normalization condition, we should obtain the eigenvectors matrix here. In the second case, we once again consider that we have distinct and positive diagonal elements for the V matrix. However, the off-diagonal components are equal and are dominant in the sense that they are much larger than this difference. So we can now work in the same method but using a new small quantity epsilon given by this ratio, and we should obtain for exactly the same approach the two roots given here. Now, to first order in epsilon, using the Taylor expansion of this expression, we can once again also find the components of the eigenvectors as given here, and of course to these equations we also append the normalization condition to finally obtain the eigenvectors matrix shown here. So we see that depending on whether the V matrix is diagonal or off-diagonally dominant, we get different sets of eigenvectors with different relationships between their components. In the case of the degeneracy, the number of independent equations among the eigenvectors is insufficient to produce the ratios of their components. Let's say, for example, that one of the roots is a double root, and then two components will be arbitrary while the others will be fixed by the eigenvalue equations. So assuming that for this specific double root lambda we have two allowable eigenvectors which are labeled by primed objects, and assuming further that they have been normalized in the sense of 622b, then we can construct a linear combination of these two primed vectors. So it's the unprimed vector L, where the coefficients of this combination are chosen in such a way that L is orthogonal to the vector of index k and the prime vector of index k. So then from 622a we can obtain the ratio of these components as being given by this contraction, or in shorthanded form by the number minus tau of index L. Now if we were to return to our example, we can let the diagonal elements to be equal, be 0, and make the off-diagonal elements go to 0. And then we obtain a twofold degeneracy of the root, so both values will be equal to 0, but depending on the order in which you take the limits, so either make these equal first and then make these vanish, or the other way around, we obtain the two sets of eigenvectors that we have seen previously, so both in the limit where the small quantities delta and epsilon vanish. So you can see that if we were to map these to the real Euclidean space, they would, in the first case, we just obtain the x and y directions, and the second case is the previous set rotated by pi over 4 about the z-axis. So these two sets are linear combinations of each other, and we can generalize this result to any two eigenvectors of the forms given here, where their components are real and they satisfy this normalization condition. So the conclusion is that there is an infinite set of possible eigenvectors in the case of degeneracy, which is something that we have encountered as well when we looked at the eigenvalues of the inertia tensor. So one other way to see these considerations is to take the eigenvectors of 630 in the limit where epsilon goes to 0 and transform V through the similarity transformation here in order to obtain the following primed matrix, where we see that it is diagonally dominant, but it has small energy terms that are off diagonal. And in any case, 6.32 implies for the normalization condition of the vector L implies this expression, and having this together with 632 itself, it means that we can calculate the coefficients C1 and 2, and thus uniquely fix the vector. And in that case, both it and a new vector k, which is just equal with the original primed quantity, in this case both of them will be orthogonal to the eigenvectors of the other distinct eigenvalues, and thus we have a complete set of orthonormal vectors. So this was an illustration for the case of a twofold degeneracy. In the general situation of an m-fold root, what we do is we use linear combinations of any m allowable eigenvectors labeled by primed quantities, and then we can take the first eigenvector as a multiple of the first primed quantity, then we take the second one as a linear combination of the first two prime vectors, and so on. And in this manner, the number of constants to be determined is equal to the sum of the first m integers, namely this number. The normalization requirements themselves provide them conditions, while the orthogonality conditions are of the number given here. So adding these all together, we obtain enough conditions to fix the constants uniquely. And really this process is completely analogous to the well-known Gram-Schmidt method for the construction of orthogonal vectors out of an arbitrary set, and it's identical to the procedure that was used for the case of double roots of the inertia tensor. To hopefully make the physics a bit more clear, we can once again look at a simple example. So we will return to the Lagrangian that we've studied previously, and now we let the off-diagonal elements of the V matrix to be 0, and we assign the values k1 and k2 to the diagonal components. So then if we write the operators t and v explicitly, they have the matrix representations given here, And then if we solve the secular equation right away, we obtain the obvious result, namely that the squared frequency for each mode is just the corresponding spring constant k divided by the mass m. And the corresponding eigenvectors we can see immediately as having the components given here. So the system described in this situation really is just a plain anisotropic oscillator. So it's a two-dimensional oscillator with different spring constants on two orthogonal directions. Now, if we make it isotropic, so if we let the diagonal components to be equal, then we can change the representation from Cartesian to polar coordinates. So we can rewrite the Lagrangian in polar coordinates as shown here. And if we calculate the equations of motion, we obtain the two well-known results. So the radial equation here and an equation corresponding to the conservation of angular momentum. And we see that if the angular momentum vanishes, then the radial equation reduces to really the equation of a harmonic oscillator. So it has a particular solution of this form, right? So it's just a harmonic oscillation where the radius of the particle goes through the origin and has a maximum amplitude of r0. Now, in the case where the angular momentum is no longer zero, then we can write immediately the energy function of the system. And remembering that if the Lagrangian is not explicitly dependent on time, this quantity is conserved. So the energy function is constant in time. And what this implies is that the equivalent one-dimensional problem corresponds to the motion of the particle in the effective potential given here. And due to the fact that h must be conserved, and so it must be constant in time, it means it is impossible for the particle to reach the origin point anymore. So the particle cannot cross through the radius equal to 0. And really this is entirely consistent with our, it's another way of stating the conclusions of our analysis in when we discussed the central force problem and the motion of a radial harmonic oscillator. Now we can look at one last interesting case, namely a case where the diagonal elements are 0 and the off-diagonal terms are constant. So then we have once again, our two matrices T and V are the ones given here. And if we solve the secular equation, we obtain one real frequency, which just corresponds to the usual oscillatory motion, but we also obtain a purely imaginary frequency, which is just so it's just ω1 multiplied by the imaginary unit. And these two modes correspond to the eigenvectors I've given here, where the first one, this one just represents harmonic oscillations with frequency ω1, while the mode orthogonal to it is one of unbounded motion, because this frequency is imaginary. So what you end up with is a mode where the particle recedes to infinity as an exponential of t divided by tau, where the characteristic time is just the inverse of the ω1. And obviously for times that are small with respect to the characteristic value, then the particle falls off linearly to infinity. So to understand what is going on, you just need to calculate I've written it symbolically here, so you can calculate the Hessian of the function v. So you can construct the potential energy from this operator, then calculate its Hessian, and you will obtain a negative value for the origin. So what you see in effect is that the origin point is a saddle point. So it's a point which corresponds to a minimum of the function in one direction. So it's a minimum in the direction corresponding to the vector a1, in which the particle oscillates harmonically, but in the orthogonal direction given by the vector a2, the potential energy is actually a maximum. So if the particle moves slightly from this point, it just falls off to infinity. In summary, we have mapped the problem of small oscillations to an eigenvalue equation in configuration space involving the simultaneous diagonalization of two operators associated to the kinetic and potential energy. We have discussed the particular case of degenerate eigenvalues and studied the example of a two-dimensional system in various limiting cases. And in the following, we are going to discuss the frequencies of free vibrations, and we will also talk about normal coordinates. So, all that being said, I want to thank you very much for watching. I hope you found this discussion worth your time, and I will catch you later. Goodbye.